It's really good to see all of you here, a lot of friends, good friends for many years, colleagues, and students. Nice. Thank you all for coming. This is the title of my talk. I'm going to throw a lot of things on you, so fasten your seatbelts, because it's a kind of a broad topic. And actually, it might have been as well, the title of my presentation could have been taken right off two issues of The Economist, the tragedy of the ocean here, and then a few years later, the promise of fish farming, the Blue Revolution. Those are things I'm going to discuss today. The seafood and aquaculture, the crisis and the promise. And the tragedy of the ocean is a direct reflection of the fact that we are adding about 200,000 people every day to our planet. This is like the world population clock, almost in real time. Look here, this is how many people were added to the world today, and it will be about over 200,000 by the end of the day, and this is will be for the year, it will be over 80 million people added to the planet. So obviously we have to feed people, we know it, and not only we have more people on the planet, but more people eat more fish. This is the increase in per capita consumption. So this is the increase in the world population, where, as you saw, we're about 7.34 billion people right now. This is the increase in seafood consumption per capita. So people go off red meat into poultry and onto seafood. And this is the amount, the increase, this is from the 1950s, of the increase in how many fish are consumed in the world, or harvested and consumed in the world. And if you think about it, fish are the last hunt and gather animal crop, right? We have these big seine nets, factory ships, huge net, again, industrial net, small fleets. This is a picture I took in China, going around roaming the ocean for the seafood. We don't do this. We don't harvest in the wild, right? Chicken, poultry, cattle, pork, we don't do it, right? We farm them, and the same has to happen for fish, which are still the last hunt and gather kind of practice. Because of everything that I said, this is the state, which is pretty sad, of the world's fishery stocks. About 61% of all our fishery stocks are fully fished, so they're at capacity. The ocean cannot give anymore. 29%, and both those percentages are increasing, are overfished. So in other words, the stocks are now going down, and only 10% and decreasing are just underfished. Those are fish that we have less interest in terms of seafood consumption. And as a result, we are facing a growing global seafood gap, which is the difference, the gap between the ever increasing demand for seafood and the best leveling off harvest or landing. So the increasing demand and the leveling off fisheries. And this is the challenge for aquaculture. Aquaculture, the farming of commercially important marine aquatic organisms in captivity. This is the challenge. It has to fill this gap. And responding to this challenge, aquaculture actually has been the fastest growing agricultural industry in the United States and globally. And for the first time, 2016, we produce as much as aquaculture production as we consume from capture fisheries. And you see capture fisheries are leveling off and declining and a little bit and so on. So aquaculture has been responding, and I don't know if you know that, but we now consume more farmed fish than beef. So it's really, and you can see the increase in aquaculture production. But it's not enough, and here's the challenge. Aquaculture, in order to meet that challenge that I showed you, aquaculture, which is currently an 80 million ton, $26 billion industry, it must increase production 2 to 3 times by 2030 to meet the challenge. For that, it has to become much more efficient, cost-effective, and environmentally responsible. Very important. For that, it has to overcome all kinds of biological hurdles and constraints, and I'll go through some of those. For that, it needs very strong input from modern biology and biotechnology, and this is what we are all about here. And when I'm saying modern biology and biotechnology, it's from the gene all the way to the fish. So let's talk about some of these bottlenecks. When I started, and I've been around, as Russell mentioned to you, for a long time in that field, in the 70s, the first bottleneck to open was captive spawning. So most fish that are commercially important, that are being placed in tanks, like you'll see in a few minutes, they do not spawn or produce in a very unpredictable manner. And obviously you cannot start an efficient, cost-effective aquaculture industry without being able of what we refer to as closing the life cycle of the fish in captivity. Producing eggs and juveniles, I refer to them as seeds, like any other crop that you're using. So that's the first bottleneck that we had to close. And bringing it close to home, the rockfish, the striped never spawn spontaneously or never reproduce when it is grown in captivity. So for that, we had to go in the early days into some tributaries in the Chesapeake Bay. We electrofish the fish that are on the spawning ground, and only DNR can do it. And you can see here some electrode that deliver very strong electric current into the water. And you can see here the fish are belly up. They are alive. We don't kill them. They're alive. We collect the mature fish. You see this female has plenty of eggs in her belly. We take them onto a truck. We drive them into a hatchery, which is a crazy practice. You cannot really rely on like a whole production developing aquaculture industry on this practice, because it's very seasonal, number one, and number two, sometimes the fish are not there. They are not on the spawning ground at all. So closing the life cycle, as I said, was a major bottleneck that we had to address. And obviously I'm now going to tell you in about 2 minutes or less work that we did in like 20 some years. So we wanted to understand, so those fish growing in captivity, and that's from downstairs below us, those tanks. So you put them in captivity, rockfish, they don't spawn. So we wanted to understand why, and we assumed that the reason is a hormonal failure, that the fish fail to spawn because there is some type of hormones that are not working. The main reason is like that the fish are not being on their spawning ground. And so it's an environmental reason. Fish, as you know, like rockfish, are migrating thousands of miles to get to a spawning ground for rockfish on the tributaries of the Chesapeake Bay. They don't have it in captivity, but we cannot simulate it. And so we went into the hormones. We thought that, the lack of the environmental condition is translated into an absence of reproductive hormone. So we did compare the entire reproductive axis. It's like, somebody referred to my work as being OBGYN, like just in fish. And the entire, this is Dinos Mailonas, one of my early graduate students here at imet. And so we took those big fish, and you see we took a blood sample to study all the hormones. We call it the brain reproductive axis. So he took a blood sample. The bad thing is holding the syringe in his mouth, and that's not a very good way to go about it. Long story very short. We narrowed it down to this hormone, the brain hormone, that is called gonadotropin releasing hormone. Never mind, it's a decapeptide produced by the brain, made of 10 amino acids. It's not being synthesized, it's not being produced in captivity. Long story very short, we synthesized very super active, potent. We did some peptide engineering. We changed things in the peptide, and we produce a peptide GnRH analogs, we call them, that are very super active, highly potent, and we put them in those small implants. Those are polymer-based delivery system, sustained release delivery system for the induction of spawning. We call them Reproboost, and you inject them into the fish. They can made in a powder. You inject it into the fish. It breaks down. It dissolves, and the hormone is delivered to the fish. You can see us here injecting it to the fish. Here is a rockfish. Here is a gilt-head sea bream, the Italian orata, Dorado Royale. Here is myself when I was younger and, darker hair, working with the salmon industry, on the net pens of the salmon industry, injecting the salmon. You have to do it, otherwise they don't spawn. And some collaboration with the National Aquarium in Baltimore. We did it for, who knows what fish this is? Sea dragons. They go for about $5,000–6,000 each, and so we did it also for for those fish, some ornamental fish, and as you can see, it's a very generic technology. Now moving to, which one is this fish? I didn't ask you, right? So bluefin tuna. Beautiful fish, but bluefin tuna is overfished big times in Japan. It's just the ceremonial first fish of the year. This year earlier, it was sold for $3 million. Just one fish, okay? So I mean, obviously there is a lot of interest in bluefin tuna. They are overfished, obviously, and we wanted to develop aquaculture and spawning of the bluefin tuna. How do you do it? I mean, how do you inject this fish? So you don't inject them, you shoot them. So those are in big net pens, and you send into the water like free divers, and they have a spear gun. At the tip of the spear gun, there are the implant, the small delivery system with a missing hormone that we have developed, and you shoot them. This is just to tag the fish. By the way, this is gone. I mean, after 48 hours, the whole thing is gone and dissolved. It just jump starts reproduction. And here you can see the tuna that were like tagged here, meaning, well, this fish got the treatment. And here are the eggs. These are like very tiny eggs, about 1 millimeter in diameter. You see the head and the tail and the embryo inside the egg. And those are some of our tanks from downstairs again. And Jorge Gomez Gerardo, who is right here, worked on this tuna, we call it larva, of growing, taking them from the eggs to the juveniles. And we all did this downstairs. And for the first time in North America, we were able to produce bluefin tuna juveniles. And here you can see the larvae. Well, these are tiny, right? They would grow to 800 pounds, those guys, And this is Jorge's. This is Jorge's hand-fed tuna. Hand-fed tuna. So I mean, it's quite impressive. And so this is something, again, closing the life cycle. Switching gears, okay? You guys be ready. I'm going to do a lot of switching gears here and talking about the blue crab, okay? This is from the Chesapeake Bay Foundation report. We know the blue crab in the Chesapeake Bay have been going, this is the abundances, up and down and up and down. And you know that this is this is quite common for like $100 a dozen. And some of you old-timers here know that it was not like that. Decades ago. At about the year 2002, we started a program on the blue crab. And again, the idea was to do something about this situation. So it was a program on hatchery production of the Chesapeake blue crab. Phillips Seafood helped us, gave us some funding. This was a close partnership with the Maryland Watermen Association. We put them in our tank. Those are our tanks downstairs with blue crabs. So everybody got, this was Bertha, this was this, everybody got their own tag. And we, the whole purpose of the objective of the project was to better understand the blue crab basic biology in the Chesapeake Bay, because it was quite amazing how for such an economically important fish, for the mid-Atlantic fish organism, for the mid-Atlantic economy and for the ecology of the Chesapeake Bay, there was so little known about the blue crab. And we were looking at stock replenishment using hatchery produced juveniles in the Chesapeake Bay and aquaculture. And first thing first, we indeed closed the life cycle, despite many people said it was not being possible to obtain year-round spawning of blue crabs in tanks. And then came the blue crab juvenile production, the real challenge from, those are blue crab larvae. This is how they look when they're spawned. And people told us, you won't never be able to get them to juvenile. Odysmora, sitting also here, was the magician here and made this all happen. And these are his hands, actually. And what he's holding are zillion of blue crab juveniles that we produce downstairs. And these are the beautiful babies that we produce here. This was the first time in the world that anybody has been doing this for the blue crab, for the Maryland species. And these are when they're like about 2 months old. We did a lot of release studies into the Chesapeake Bay. And here you can see it was a big partnership. You'll see in a minute. We are releasing them to some of the natural nursery grounds of the blue crab in the Chesapeake Bay that were big way under the carrying capacity, so they could have taken more crabs. And then we were like monitoring their whereabouts, and we were trying to catch them, and we used DNA fingerprints developed by Alan Place sitting here to tell if the crab that we catch came from a hatchery or from the wild. So long, very intensive program. I think we had about 80 publications altogether. This is one of them. You can read much more about it. The Chesapeake Bay blue crab kinetic substitute is a multidisciplinary approach to responsible stock management. And my point that it was a very, very kind of multidisciplinary partnership with the Smithsonian Environmental Research Center, on the Road River, Tuck Hines, who is very known crab ecologist, us people here, people from so I said the CERC, on the Road River, the Virginia Institute of Marine Sciences, scientists from NC State, so it was really all around the Chesapeake Bay type of and a very successful program, which provided a lot, and I think we can take, some credit for some of the rebound, just not because we released them to the Chesapeake Bay, but because we provided policymaker real biology facts and, migrating corridors of the blue crab, so they can make educated policies educated decisions in managing or developing policies to manage the population. Switching gears again, okay, to another, back to fish and to another bottleneck, constraint. Nutrition and feeds is a big problem in sustainable aquaculture. Harvesting fish, the issue is harvesting fish to feed fish, and I'll explain in a moment. This is like the pellets, how the pellets look when that we use to feed the fish. And the problem is that they are heavily dependent, this feed is heavily dependent as it is now on fish meal and fish oil. So here are the facts. 1/3 of all fisheries harvest, global fisheries harvest, these 90 million tons harvest globally, are reduced to fish meal and fish oil. So your menhaden and anchovies, sardines, and other forage fish are reduced. And if you do the math, you have to harvest 2 to 3 pounds of fish in the wild to produce 1 pound of fish in aquaculture. Doesn't make sense, right? So, and not only we're running out of, obviously, the fish, but also the prices of fish meal and fish oil, so oil coming from fish, forage fish, or meal proteins coming from fish, they are going up, so they are not becoming affordable. So we must find replacement for fish ingredients, and we have been doing it here for many years. And again, Alan Place sitting here is the lead faculty member in this research. I'll give you just one example. Cobia, it's a highly carnivorous fish that needs a lot of fish meal and a lot of fish oil. The same is for salmon. But Al developed a diet, and his student, Aaron Watson, they developed a diet that has no fish meal or fish oil. They use all kind of replacement. We will talk a minute about it. And the fish grew faster with a new no fish meal oil diet, and those are carnivorous fish, right? They eat fish in the wild, then compared to the commercial diet. And not only that, you hear a lot about fish being contaminated. They have PCBs and mercury, especially people say in aquaculture this is the case because fish meal and fish, mainly fish oil. So we reduce fish into oils that contains PCB and mercuries and so on. So here is the commercial diet. They have higher level. We go 1/3 to 1/3 of the levels with the diet that have no fish or no fish oil. Levels that are way beyond, the allowable level. So not only you're like avoiding the over-harvesting and so on, but you are obviously reducing contaminant, which is a very important point, using no fish meal, no fish oil diet. So there are different sources for replacement of the fish meal and fish oil. People use some plant meal, some protein meal. I'm saying there are proteins and insects are being used, but we like very much to use microalgae as a source of oils or proteins for aquaculture feeds to replace, because for instance, many of the good ingredients that we have in marine fish, like omega-3s, are coming from the basis of the food chain, which are the marine microalgae. So this is again from our facility downstairs, our algal production, and so still going, but a lot of good news here. Growth. Now, what is the issue with the growth? We also always want to make sure the fish grow as fast as possible to the market side. So I'm going to throw some provocation, controversy at you. One way that you heard probably a lot in the news is the use of genetically modified fish. Here it is. Which fish you think is the genetically modified one? So here's the salmon. Aqua Advantage salmon was approved recently by the FDA and compared. So I mean, what do you think? Is it a risk or an opportunity? I'll show you a few things before you answer. FDA approved. It approved those fish for consumption and for production, although, as you see in a minute, not yet in the United States. In November of 2015, after over 20 years of debates and so on. Do you know what was the first plant that was the first genetically modified plant that was approved? It's the flavor saver tomato. It took about 18 months. It was the first one. This took about 23 years. Why so long? Because of this. Okay, because Frankenfish. This is Time magazine. Okay, year after year, or every time that FDA made some type of milestone, and I was involved in the process with the FDA. This is again, you know, Time magazine. Frankenfish. Would you eat genetically altered fish meat? And then 3 years later, Ben GMO salmon, Frankenfish, and so on. Now, before you tell me what you think about it, here are some facts. I don't know if you knew. Over 80% of all planted crops in the US are genetically modified. You'll see the numbers in a minute. Over 75% of crop-based foods on your supermarket shelves contain GE ingredients. If you take cereals in the morning, soups, tofu, do you drink beer? Okay, so, and here are the numbers, okay? 90% in the United States, 90% of the corn is genetically modified. You can read it for yourself. I mean, everything. I mean, and many vegetables and fruits, and nobody blinks twice about it. But why is the big problem with salmon? And actually, there have been selective breeding of salmonids and many other fish for many years, and it changes more genes. This genetically modified fish is just only adding one copy of the salmon on growth hormone, one copy. And it doesn't grow, by the way, it doesn't grow larger, it grows faster, so faster to the market size. And so the FDA approved it, and Canada said, okay, we are ready to sell it. Fish genetically engineered salmon sold in Canada, and you can see again, no problem with Canada, but here's the situation in the US.
We refer to this GE salmon as Frankenfish.
Okay, did you hear what Senator Murkowski is saying?
We refer to this GE salmon as Frankenfish.
Okay, and this is relatively recent. After all scientists in the world, and I'm going very short here, said there is no problem, after FDA took 20-some years to approve it and said it was okay, no risk. This is what she's saying, okay? And this is why it's on hold in the United States.
We refer to this GE salmon as Frankenfish.
Okay, and this is not long ago. And that's what she is saying, and this is why it's still on hold in the United States. Stay tuned. Okay, switching gears, moving to aquaculture and the environment. So 95% of aquaculture fish farming practices are done this way. So we are growing fish this is salmon, in a beautiful fjord in Norway, in what we call floating net pens or floating cages. And there are many issues with them, and those are some of the issues, and I'll be, again, very brief. I mean, chemical pollution, the waste produced by the fish, it's like runoffs. You feed them a lot of food, there are runoffs to the marine environment, right? Biological pollution is a big problem. Fish escape, and those fish are different. I'm not talking about genetically modified, but if you selectively bred salmon for 20 generations, it's different from a wild fish. And when you grow Atlantic salmon in the Pacific Northwest, which they do, and they escaped not too long ago, well, they go to the environment, it's a biological pollution, they interbreed with the wild stocks, or they establish themselves. So it's a big, big problem. Disease transmission, aquaculture has been actually blamed for transmitting diseases into the wild stocks, but actually the other way around is more true, that, you know, fish in those conditions are being susceptible to diseases that are in the marine environment. So for all these reasons, we developed we chose to develop alternative sustainable aquaculture. And as you can see, and this is from my title on, everything that we do here at imet on aquaculture has the mantra of environmental sustainability to it. And okay, we'll take you for a little bit of a virtual tour in our facilities downstairs. So land-based, we are developing land-based, fully contained, recirculating aquaculture. So what we do, we start, these are our tanks downstairs. We start with city water. We remove, we use carbon, charcoal filters to remove chlorides or whatever. So we start with water that are cleaner than the water that we drink. We make any salinity. We can simulate we can do freshwater, of course, but we can do we can simulate the Gulf of Mexico, the Atlantic, the Pacific, the Mediterranean, and so on, and we recycle the water. Okay, now the benefits of those fully contained systems that they generate no waste. They are disease-free. There is no disease because by definition, you know, they are contained. They are very clean, no contaminants coming from the marine environment. They are flexible, very important. You can do warm water, cold water. You can do high salinity, you can do low salinity, and it's just they are generic. If you are in Maine, you can grow cold water species, Atlantic salmon, cod. If you're in Florida, you grow warm water species. Here, we grow dozens of species downstairs, and that's the beauty of the technology. They are biosecure. There is no escapees. So you can grow whatever you want. Actually, if it was the genetically engineered salmon, it's only allowed in this type of system. And they are applicable for rural and urban locations. We'll talk more about it. And you can put them next to your airport. You can put them next to your main market. You can put them in the Midwest. And you reduce your carbon footprint. Again, it's a work of many, many years. It's all about, so we work on fish, but it's all about the microbiology. Those kind of cylinders, we call them the life support system. There are a few of them. There are biofilters where there are beneficial microbes, microbial community and beneficial microbe that live in symbiosis with the fish that are in the tank. And they clean the tank. They consume, they live on the waste produced by the fish, and they clean the water. So it's and the water recycle again and again and again. So zero interaction with the environment and no waste produced to the environment, but the other way around. We don't introduce any pathogens, any contaminants, and so on. So it's a work of obviously it takes a team, it takes a village, a city, and so there are many of us working on those systems here. This is downstairs. Those are two tanks, some of our pilot tanks that are 12 foot in diameter, 3,200 gallons each. Small one. Just look how clean the water is. So very clean water, so those are like warm water fish. This is the gilted sea bream, the French dorade royale, and because it's a non-native species, this is the only practice where we are allowed to do it, and it has an economical opportunity here because you are really you only compete against fish that are being imported from overseas, and you produce them right here on site, and you'll see some of the benefits in the meantime. The fish grow, high density. You look into the water, very pristine water, and it is the same water for the entire grow-out cycle, and look how pristine they are, look how beautiful the fish are. And this is very important. Okay, this was data that was very difficult to get on this, like high-value marine fish that we just saw. This is our system, okay? We grow them to about commercial size, a little bit under a pound, in about 8.3 months. And this data was really difficult for me to obtain. This was from the net pen production of this fish in the Mediterranean. And you know, they didn't produce this, we produced them larger to 1 pound, but so you can see here that it takes about, for the same size fish, about 19.3 months. So double the time to produce those fish. And you see there is a slow, I mean, because there are winters and so there are summers, there are winters, there is slowdown in growth, and we keep the fish, this is the idea, we keep the conditions optimal for the best performance of your fish of interest on a year-round basis. So so this is why they grow so much faster. Now, diversification is a key word to success in aquaculture. You know, your chicken, there is chicken, right? Although, you know, we know Jim Perdue, we talk with him from time to time. He tells us there is this type of a chicken and this type of a chicken, but I don't know. But fish, I mean, the opportunity in aquaculture is to diversify, right? So, and so we are diversifying. You'll see in a minute to bronzini. You can name the species. Salmon, you saw blue crabs, and we work here on oysters. I don't know if Colleen Burge is here, but she's there. She's working on oyster aquaculture downstairs. And so we can do all those and everything in containment, and you can diversify. This is the opportunity that those systems allow you. Here's another high value fish. I don't know if you know, who knows this fish? Oh, we mentioned it before, but you don't say. Cobia. Cobia is a high-value kind of cosmopolitan fish. It's in the Pacific, Atlantic, a lot in the Gulf of Mexico, fished out. And we worked with this fish quite successfully. So here's like, who knows this fish? This is from downstairs. Instead of taking all of you downstairs, it's the bronzino. So we were the first one really to bring the bronzino into this country and develop the whole aquaculture of this fish, high-value marine fish. And it grows very well, and we are harvesting them, and here you can see them loaded into ice and totes into J.J. McDonald, who was one of the partners of the work that we do here, and from here they went to the DC Central Kitchen, in this case, where it went to the chefs. So you know, the DC Central Kitchen is teaching people from underprivileged backgrounds, from poverty, to become cooks, to become chefs, to feed the community. And many of these fish have been going also from here over the last couple of years to homeless shelter and so on. So this is a very important program here. I just forgot to mention, I showed it here, Keiko Saito sitting here. She is the person who is like the principal investigator on this bronzini project. But again, you know, there is a lot of people from the Institute involved. This is for a few years ago. We also work with restaurants in the city. Some of the best fish restaurants, they are dying to get fish from us, and they very much appreciate the freshness factor. We harvest the fish, and 3 hours later, they're being served. I don't know if you know that when you go to a restaurant and you eat a bronzini that comes from Greece or from Turkey, or oftentimes they are like 1 week post-harvest. Easy. And those are obviously, so there is the big benefits of producing, and even the Baltimore Sun thought that we did something good. So Rona, where are you? I mean, this is Tim Wheeler, right, wrote this story back then. So, and this is another fish that we are focusing now quite a bit on, this is Atlantic salmon, and here's the need and the opportunity in the US for Atlantic salmon. And, you know, like from now on towards more or less the end, I'm going to focus on Atlantic salmon. So the US is the world's largest importer of seafood. I don't know if you know, but close to 90% of the seafood consumed in this country comes from overseas. Seafood imports contribute about 17 billion annually to the US trade deficit, the largest among all agricultural imports. It's pretty big. 95% of the salmon consumed in the US come from overseas. So at a value of about $3.4 billion. So this is the opportunity This country imports about $3.4 billion Atlantic salmon into this every year. So there is an opportunity. We should produce them locally, right? Right now, responding to this situation, as we speak, there is at least a $1 billion investment in land-based Atlantic salmon production in the United States, and we'll talk about it. And here are some of the states. There is Atlantic salmon production. Many cases it's still a plan and it's still in the permitting process and so on, but major investment in Maine, in Florida, in Virginia, Wisconsin, Indiana, so Midwest, state of Washington, California, and Maryland. So I'll show you some of those projects. So we're talking about huge production in salmon in warehouses. So the same type of practices that we developed downstairs that I mentioned to you earlier. So huge production in warehouses. We're talking about 10,000 ton production in one place. That's about 22 million pounds. And this is Miami. It's a company by the name of Atlantic Sapphire that is investing about $200 million. In stage one, they're talking about this number, and then they want to 10 times more, to produce 10 times more fish. And they have like 36 tanks that are about 450,000 gallons each. So we're talking about large scale. And I was there a few months ago, and it was like a huge construction city. Now they have some fish in the water, but it's Miami, and this is salmon. So salmon is 14 degrees, so it's 55 degrees, right? And you're talking about Miami. This is one that is up and running, though, in Superior Fresh in Wisconsin. It's a 6-acre building. They do aquaponics, so they produce Atlantic salmon, and they use the waste to grow leafy greens, and they're very successful, and they're going slow, 1.5 million pounds, which is what they target. This is Steve Sommerfeld, our friend. He's kind of their engineer, scientist, and everything else. This is Aqua Bounty, the same company that developed the Aqua Advantage transgenic salmon, but they are like in the land-based salmon aquaculture trade. They are not, or business, these are not genetically engineered fish, but they have in Indiana 5 million pound facility here. Those are smaller tanks, only about 70,000 gallons each, many more tanks, and you close up, you see salmon here, very, very high density. And right, go Maryland. American salmon, Cordova, Maryland. We have here Chris Haleb, who is one of the founders of the company. And we have several people from Commerce here, Ewing and others. Thank you for coming and for helping in that. So, right, the future of aquaculture is in Maryland. And this is the site that they have. It's about an 80-acre site in Cordova, just a small community next to Easton, and they're talking about 200 million plus investment. Phase one will be 5.3 million pounds per year production. Phase two will be about 21 million per year production. And so this is the site, this is one of the building. I'm going to zoom in because it's really important. It's called Applied Aquaculture Research Center, and their nursery and hatchery and applied. So our center downstairs, we call our aquaculture facility Aquaculture Research Center. Downstairs, I showed you a lot of pictures. This is the Applied Aquaculture Research Center, so a big kind of extension of what we do here. And very recently, there was an MOU of collaboration signed, executed between between imet, UMBC, and American Salmon. I think that the difference between success and failure in this system will be keeping on top of the most recent development, cutting edge research, and that's what American Salmon decided to do, to work with us and be ahead of the crowd in terms of the technology, the new platforms, and so on. They're going to use Veolia's technology. Veolia, as you know, is the big water company, right? And so Veolia is in aquaculture for the last few years, and they developed this concept of one tank, and you can see it here, like you see the scale of it. Those are people here, that is 160 foot in diameter. The other ones I show you, the biggest one were 60 foot in diameter. And they produce, just one tank will produce 2.6 million pounds of fish. Huge production and state-of-the-art technology. And here you can see they have already a couple of systems working in Europe, mainly in Norway and in Denmark. And here you can see it's a very clever system which have different rings. It's all recirculated, as I mentioned, and fish grow from smaller to larger. And we are working with American salmon and Veolia to improve the containment, to improve the recirculating of the water, and so on. And there is a lot of investment going on in Maine between two companies, Whole Oceans and Nordic Aqua Farms. Both are like owned by Scandinavia, so it's all coming from, I'll talk in a minute about Norway, and those guys are planning all together to start or to get to 7 million pounds of fish, 70 million pounds of fish. It's a lot. Right now they're talking about $350 million of investment between Maine and California. So what's the main hurdle? The main hurdle is to remove the waste. Fish produce waste. There is no way around it, and we develop technologies to remove that waste in a way that is environmentally sustainable. You don't want it to go to the environment. And here's a quick fact. One farm of these biggest farms will produce hundreds of tons, hundreds of thousands of pounds daily of organic waste, of sludge, of the organic waste. What do you do with that? And that was, and everybody is calling us, and everybody, because this has been our approach. imet solution, use methanogens. Methanogens, as the name implies, those are microorganisms from the marine environment that produce methane, that produce natural gas. Use methanogens to convert organic waste to biogas, to methane. And as you can see here, it happens. So the idea is to simulate natural processes that occur in the ocean that produce flammable, combustible, biogas. So this is the idea. And this is mostly the work of the lead scientist here is Kevin Sauer, sitting here as well. And this is our strategy. So we start with the fish waste, because in the fish waste, there is already some methanogens that are there, naturally occurring. And we are starting to enriching, so we are getting the fish waste, putting it with different types of media and different types of temperatures and conditions, and we wait for those and we try to accelerate it, and we wait. You see here we can suck out some of the, this is all vacuumed and sealed, and we can suck out some of the gas here and look for methane production. And 30 days later, you see the methanogens are taking over, and they're getting rid of this waste, okay? So, and again, I'm telling you very very much simplifying a very long story, because those communities are quite complicated, and it takes, a lot of studies and analyzing to get to identify those communities. And And then and once we have enriched, as I said here, once we have enriched the methanogens that are naturally present in the fish waste, we go and we scale them up. And this is from our 5th floor here. This is a fermentor, very unique, about 250 liters, so it's about almost, 65 gallons. Fermentor where you can put, a sample of microbes there, and you scale the production up. Again, sounds simple, but it's not. And then you harvest them down to those canisters that are like 20 liters from this, and then we get the community analyzed and concentrated, and we inoculate them. Now this is ours. It's a very little 250 gallon from downstairs bioreactor. Here's the fish tank. So we inoculate it with the microbe, and the organic waste from the fish tank comes from here, and the biomethane comes out from there. Very simple, right? And it's totally flammable, as you can see here. Right off the fish tank, we produce flammable fuel-grade methane, biogas, natural gas, and we can even start right off the fish tank. This is a methane-driven generator, so we can start a generator and generate electricity right off the waste. And it's very, very, very efficient process. This is just some beautiful pictures and then from downstairs. So, Norway heard about our work. And Norway is the world's largest producer of Atlantic salmon, mainly in net pens, but they go more and more into land-based because of all the things that I said. And anyway, the first stages of salmon are being grown land-based and not in the ocean. Norway has about $8-9 billion of Atlantic salmon industry, so they called us. Cermaq is one of the biggest companies in Norway, and their latest operation we call them small salmon production, they need it because Norway is changing. So they used to be able to release all the waste to the fjords, no problem. But they are changing now their policies and the laws. And if you are a new operation like this was one, and they're producing 2.5 million pounds of fish annually, it's a lot of fish, and also the young salmon before they go into the floating net pens, you have to treat at least 50% of your solid waste in a way that is environmentally responsible. So they were a little bit kind of under the pressure. They had to do it very fast. They contacted us, Kevin and I, and Keiko and others, were involved in the process. And they produce a lot, because here's the amount of the solid waste that they produce, about 60,000 tons of pounds of sludge at a 5% dry matter daily. They had to do something with it in a haste. So we told them, okay, well, and this is inside the facility. We told them, okay, send us some of your waste, fish poop from Norway here, because we are really tailoring the microbes to the fish of interest, to what they are being fed with, and so on. So they did. They sent it to us, and we started to do, as I showed you before, like enriching the microbes and so on. In the meantime, we were talking to them about, now we are not talking about a 250-gallon, bioreactor we have downstairs. Now we are talking about 25,000-gallon bioreactor that they build in Norway based on discussing with us and our specs and inputs and so on. And in the meantime, they were building this bioreactor. The first commercial scale one in Norway, which is the kingdom of salmon. Here you can see it. And again, starting with the salmon poop, enriching it, as I saw you earlier. Here's Kevin Sowers by the fermentor. He's now harvesting the scaled up, the biomass of this consortium of methanogens that we scaled up into a 20-liter canister that was shipped straight into Norway, 2 days shipment, whatever. And here is Kevin on the bioreactor, just inoculating the bioreactor. You will not recognize him here, but it's him, and Keiko was there too. So we go there and we inoculate the bioreactor, so the microbes are there to start digesting the sludge. And we went here. This was, I think, sometimes in February of last year. We started to inoculate, and nothing much happened. So we decided to do another batch, and we inoculated another batch maybe a little bit over a month later, and then they took off and they started to produce biogas. And rate of biogas production was to 170 cubic meter per day, about 46,000 gallons per day of biomass produced at a methane content. So the biogas is not only methane. Natural gas is not only methane, but 60 to 65% is flammable, it's combustible. It's like you can start a generator. So what they do in Norway, biogas is used to heat water. They are in northern Norway, very north part of Norway. They have to heat their water, so they installed a whole battery of methane-driven boilers. They use this methane to heat their water. And if they have any excess methane, which may happen, they have to flare it. So you flare it out so it doesn't go to the environment. And this is it. This is now our state of the art. Again, I'll just finish with this last slide from, again, our beautiful fish downstairs and the pristine water. I think this is, like as it was in one of my first slides from the Economist, this is the blue revolution. And I want to thank you very much for your attention.